Methanol is an important alcohol with many uses. It can be manufactured from carbon monoxide and hydrogen according to this equation over here. It is quite clearly an exothermic reaction with 3 gas moles on the left and 1 gas mole on the right. State and explain the conditions of temperature and pressure that should maximize the yield. So I want to get as much of this stuff as possible, which is the methanol. So the temperature, the forward reaction is exothermic. Therefore, cool temp favors exo, and cool temperature is my answer. Simultaneously, I am going to, for pressure, high pressure favors least gas moles, not any old moles, gas moles, therefore favors forward. Why? Because I have got 3 gas moles going to 1 gas mole. So I would like a high pressure. Draw a labeled sketch graph of reaction rate versus time indicating the following. Now the important thing here is that you are doing a rate graph. You are not doing the concentration of any of the substances. So when you have a rate graph, let's just call it reaction rate, and over here we have got time, and we start off, oh, that's not ideal really, just erase that there and put the time axis down there. Right, let's try again. So I'm going to start with none of the forward reaction is going to slowly go slower and slower and slower until it reaches a certain rate, whilst the reverse reaction is going to go faster and faster and faster because I'm going to be making more of the methanol, and therefore I will be able to start going backwards. So that's reverse and that's forward. These now stay at a constant rate for a period of time, and the time is at 5 seconds they reach equilibrium, and at 10 seconds there's going to be a disturbance. The disturbance that occurs, the reaction rate reaches a state of dynamic equilibrium within the first 5 seconds. Dynamic equilibrium is defined as that point where the rate of the forward reaction is equal to the rate of the reverse reaction for a reversible reaction in a closed system. That comes up a little bit later. At 10 seconds, the temperature is decreased. That means the rate of both reactions will be decreased. And 2 seconds later, equilibrium gets reestablished. But let's first do this temperature decrease. If I decrease the temperature, I am going to land up favoring the forward reaction. So the reverse reaction is going to decrease a lot, and the reverse reaction will decrease a little because I'm favoring, you might have a little bit of an angle on those, it's fine, because I'm favoring the forward reaction. And at that point, I'm going to establish a new equilibrium. There it is. Here, I'm going to need to come up to a new equilibrium. So, that is going to happen after 12 seconds because it says 2 seconds later. And then it says at 15 seconds, something else is going to happen. What is that? Some CO is injected into the container. If I inject CO into the container, I will favor the forward reaction. So I will end up, the pressure will increase, both reaction rates will increase, but the forward reaction will be more favored than the reverse reaction. So I'm going to favor forward. Both reaction rates will increase because I'm going to have more pressure, and I'm going to land up flattening out again after 2 seconds later, I think, so that's 17 seconds. And I'm going to bring this guy back down again to flatten out over there so that the rates are equal at 17 again. And that is your description. So let's just go through over here. I needed to see that you started with a fast rate of forward that came down to a rate of even. and a slow rate of reverse that came up to a rate of even. Then I needed to see that when the temperature was decreased, both rates decreased, but the reverse decreased more and the forward decreased less. Then I needed to see that a new state of equilibrium was reached. Over here, when you add some more CO, the pressure gets increased. Both rates increase, but the forward increases more because the forward reaction is favored, and that would be your 2 ticks. Both increase, but the forward increases more, and I think that might be, no, and then we have a, no, that's it, 1, 2, 3, 4, 5, 6, 7, 8, 8 marks. Then we're going to say, suppose that equal amounts of carbon monoxide and hydrogen are placed in a container and then sealed. The graph shows the number of moles of CO, how it changes with time. For every 1 CO, I've got 2 hydrogens reacting. So the hydrogen will decrease at double the rate of the CO. It will change at about the same point. This isn't the most accurate graph. But that's what happens with the hydrogen. It needs to decrease at double the rate. Then it says to you what will happen to the methanol if the Kc is high. I will get lots of methanol if the Kc is high. And conversely, if the Kc, whoopsie, I don't think that's going to work. Yep, put that back. There we go. And if the Kc is low, I will get very little methanol. Here we've got the contact process initially, and it's really a bit of a rice story, so I'm just going to go straight into it. So start, used, end, volume, concentration. The start, used, and end are all number of moles. Volume is 2, which was quite convenient. Let's write our balanced equation. There it is. Whoop, whoop, whoop. So I started with 8 moles of SO2, X moles of oxygen, nothing of the product. Then they are placed in a 2 decimeter cube container and sealed at a specific temperature. At equilibrium, there are 6 moles of, of SO3. And then my link is between used of reactants and made of products. So it's 2 is to 1 is to 2. So it's 6 is to 3 is to 6. 8 minus 6 is 2. X minus 3 is that. And then you're going to say equilibrium for concentration, it's number of moles divided by volume. So this is 1, this is 3, and this is X minus 3 over 2. Now we need to look at our Kc value. Not particularly difficult. Kc is equal to concentration of products raised to the power over concentration of reactants raised to the power. And I land up with 9, because they tell me the Kc value, is equal to 3 squared over 1 squared and X minus 3 over 2. Rearrange all of that and X turns out to be 5. What is it? Well, it's a number of moles, so it's 5 moles. No further calculation required. The X was a number of moles in the first place. We've got an amount of NO2 and it's been sealed in a syringe. The volume is 80 centimeters cubed. 80 centimeters cubed divided by 1,000 is 0.08 decimeters cubed. Keep that in mind. After a few minutes, the gas displays a yellow-brown color, which is really just a mixture of these two over here. Define chemical equilibrium. Well, there are a whole lot of things for this chemical equilibrium business. The first one is that you need to have a reversible reaction. And you need to have it in a closed container. And only then can you tell me that the rate of the forward reaction is equal to the rate of the reverse reaction. If the temperature of the reaction mixture is decreased, the color of the gas mixture becomes noticeably lighter. That means that forward is favored. Classify the forward reaction as exothermic or endothermic and explain. So forward favored. Then we are going to say, they said to us, the temperature was decrease. Decrease temp favors exo. Therefore, forward is exo. At equilibrium, the concentration of nitrogen dioxide is given, and the equilibrium constant is whatever it is, 20. So we're now going to land up going, and we are going to say that Kc is equal to concentration of products over concentration of reactants. Concentration of products is, I don't know. Concentration of reactants was 0,2. They gave that to me, and I have to square it, and that is all equal to 20, and therefore X, which is the concentration of N2O4, is 0,8 moles per cubic decimeter. Calculate the number of moles of N2O4 in the gas syringe. So, number of moles is always equal to concentration times volume. I have worked out a concentration. It is 0,8. The volume is 0,08 because we worked that out right at the beginning. And that turns out to be 0,064 moles. Calculate the number of moles of NO2 in that gas syringe. Number of moles is equal to the concentration times the volume. And the concentration is going to be equal to 0,2 because they gave it to me. The volume is 0,08, and I land up with 0,016 moles. Then if I draw up a little rice table on this, I find that I have got at equilibrium 0,016 moles of NO2, and I had 0,064 moles of N2O4. So this is start used at equilibrium. Sorry, I'm lying about that. That should be at equilibrium. But I know there's a link between the used of the reactants and the made of the products. This is a 1:2 ratio, so 1:2. 2, I need to double that number. I get 0,128. So if I had 0,016 at equilibrium and I use 0,128, I need to add those together to get 0,14 moles that I originally placed into the gas syringe. Identify a disturbance to the equilibrium that produces the changes illustrated by the graph below. It's a rate versus time graph. The forward reaction and reverse reaction start off at the same rate. Something happens to hugely favor the reverse reaction, but the rate of both reactions increases. So let's write stuff that could get us marks. Both rates increase. Let's think about this. Delta H is greater than 0. That means that that is an endothermic reaction. The reverse is favored because the reverse is the dotted line and it's gone up a lot more than the other one. So the reverse is favored, which means I would have had to have, in order to favor reverse, which is XO, I would have had to have cooled it. That would have taken both reaction rates down. That's definitely not what happened. So it's got nothing to do with temperature. Let's look at pressure. I've got 2 gas moles on this side and 4 gas moles on this side. Increased pressure favors forward. Favors reverse. Because it will try to go to the side with the least gas moles. So this graph is showing me that I have got an increase in pressure. Identify the disturbance that produces the changes illustrated by this concentration versus time graph. Concentration versus time is something different. Let's see what happens here. Firstly, I've got chlorine and NO going down, whilst I've got NOCl going up. That means I have favored forward. This time you can see quite clearly with concentration, if I've changed pressure, all of the concentrations would either increase or decrease because it would all get squashed together or it would all get pushed apart. That has not happened here, so it is not pressure. It is also not adding Cl2, NO, or NOCl, because we can see quite clearly there's no dramatic changes in any of those over here. So firstly, the forward has been favored, but there are no dramatic changes in anything. And what else do I know over here? I know that forward is exo. Therefore, in order to favor forward, I must have decreased temperature.